Welcome back, everyone, to the afternoon session. And next up, we'll have Quanquan Lu from Yale telling us about the power of graph specification and the continual release.
Thank you for the introduction, and thank you very much to the program organizers and the workshop organizers for the invitation. It's always a joy to be back at the Simons Institute in Berkeley. So today I'll be talking about some very recent work on the power of graph specification in the continual release model. And this is joint work with a number of wonderful collaborators, Alessandro Aposto, Tamalika Mukherjee, and Felix Zhou, who's also my student at Yale. Okay, so to start, I'm going to give you some brief motivation for why we care about graph privacy. Which is the focus of today's talk. One of the reasons why we care about graph privacy is because a lot of sensitive information could be encoded as graphs. And specifically, the sensitive information are the connections that are the edges in these graphs. So here are some examples of some sensitive connections between individuals. So these sensitive connections could include social relationships, financial transactions, disease, for example, COVID transmission networks, and a variety of other different things. And to further drill in, why do we want privacy on graphs? There have been a number of privacy attacks that have focused on de-anonymizing a lot of these sensitive connections in these graphs. So these de-anonymization attacks have focused on re-identifying anonymous nodes in social networks and computer networks. So here is a small sample of the number of attacks that have occurred on private graphs. So I want to highlight this example here, which is the link prediction challenge hosted by Kaggle. So the Kaggle Social Network Challenge, which happened in 2011. So it was one of the first ML challenges that focused on trying to get people to come up with ML techniques for predicting links in social networks. But the problem with their challenge is they used a publicly available network. So these researchers here were able to de-identify the network that they used. And once they de-anonymized the network, they were able to find out all of the links in the network without using any ML. So they won this challenge purely through privacy attacks, and no ML was involved. Okay, so these preserving private graph information is important. And one of the ways we can preserve the privacy of individuals in graphs and these sensitive connections is we can pass a private graph into a trusted curator, which is a server with some private algorithms. And this trusted curator is responsible for answering queries from a number of individuals. So these individuals could be researchers, governments, business owners, but they also could include malicious adversaries who want to do some damage with your sensitive information. So this curator is responsible for providing answers that kind of prevents the damaging effects that malicious adversaries can do. And specifically, we want these answers to satisfy this definition called differential privacy, which is essentially known as a gold standard for privacy preservation. Okay, so before we go into the definitions of differential privacy and our description of the results, let me define some notation. So I'll start with some of the more controversial notation, okay? So the first one is epsilon, okay? So I want you to think of epsilon. So the epsilon used in this presentation is going to be the privacy parameter. So forget all the times where you use epsilon for the approximation factor. This is not what it is in this presentation. It is a privacy parameter, okay? And when I use DP, I mean differential privacy, not dynamic programming, okay? And if you forget any of these definitions, I've conveniently written them down here on the boards too. Okay, so now the less controversial definitions. Since we can't use epsilon for the approximation factor, I will be using eta as the approximation factor. And I'm going to be talking about streams. So I'm going to define these streams as S in this presentation. And this is pretty standard. So I'm going to use n as the number of vertices and m as the number of total edges in the entire stream that you see. And finally, I'll be using these abbreviations UB for upper bound results and LB for lower bound results. Okay. So now the formal definition of differential privacy. So a differentially private algorithm is a randomized algorithm. You cannot have deterministic algorithms. They are impossible. You can show they're impossible to be differentially private. So it's a randomized algorithm. And a randomized algorithm alpha A is epsilon differentially private if for all pairs of neighboring graph inputs. So I'll define neighboring graphs shortly. So for all pairs of these inputs G and G prime, and all possible outputs Y of the algorithm, the probability that the output of the algorithm run on G is in Y over the probability that the algorithm run on G prime is in Y. So this ratio is bounded by e to the epsilon. Okay. Yes.
Neighboring graphs are graphs would differ in one edge? Or
So neighboring graphs I will define after this slide. Yes. So neighboring graphs are basically defined in terms of the property you want to essentially hide using your differentially private algorithm. So I'll define neighboring graphs right after this slide. Okay, so this is a definition of differential privacy. And what do we mean by neighboring graphs? So there are usually two common notions of neighboring graphs that we use. So the first one is edge neighboring graphs. So edge neighboring graphs differ in exactly one edge. So you can see in this example here, G is this graph on the left. G prime has this additional red edge. Okay, so this essentially means that you can hide the existence of any one edge in your graph if you have an edge differentially private algorithm. Okay, so now we have these no neighboring graphs that differ in all edges adjacent to any one node. So in this example, you have G and then G prime. So G prime has this node here. So it can differ by all of the edges adjacent to this node. Okay, so what this means is if you have a no differentially private algorithm, it hides the existence of any one node in your network. So for example, if you have a COVID transmission graph and this is a super spreader, now you don't know any of the connections of the super spreader to anybody else in the graph using your no DP algorithm. So in this presentation, we'll be focusing on streaming, the streaming setting. And in the non-private setting, we have what are called these online streaming graph algorithms. So these online streaming graph algorithms continuously release accurate graph statistic after every update while using sublinear space. So there's a variety of algorithms for a number of problems that were created in the non-private setting. So you have independent set, dominating set and matching, and edge coloring. Okay, so the private equivalent of this online streaming model is the continual release model. So for the continual release model, you're given a stream of T edge updates. And you can also define continual release not in the graph setting, but because we're talking about the graph setting here, I'll define it in terms of graphs. So you have T edge updates, which could be insertions of edges or deletions of edges. And you want to produce a vector of T outputs one after every update. Now, the key here is your vector of outputs needs to be epsilon differentially private. So now you have two different releases. Each of these releases is composed in a vector, and that vector has to be epsilon differentially private on neighboring streams. So I'll also define neighboring streams right after this slide. And specifically, for this paper, we care about edge neighboring and node neighboring streams. So I'll define these. And the majority of results focus on insertion-only streams. So when I say streams later on in this presentation, I mean insertion-only streams, unless I say otherwise. And insertion-only streams only contain edge insertions or this spot, this empty symbol for denoting an empty update. And the empty symbol is useful for us when we're defining neighboring streams. So what are these neighboring streams? So we have edge neighboring streams that differ in one edge insertion. So for insertion-only streams, they differ in one edge insertion. So you can see here S and S prime, this S prime has one additional insertion compared to S. And we also have no neighboring streams that differ in all edge insertions adjacent to any one vertex. So here, your neighboring stream S prime contains a bunch of edges that differ that are all adjacent to this vertex V. So you differ in all the edges adjacent to V. So they're equivalent in some sense to the edge neighboring definitions and no neighboring definitions we defined earlier on any prefix of the stream. So any induced subgraph on each prefix of the stream. And for simplicity, we'll just redefine edge DP to mean differentially private on edge neighboring streams, node DP to mean differentially private on node neighboring streams. Yes? Yes, it's for any timestamp t. So you're looking at the equivalent updates for each timestamp t. So you can only differ in one timestamp for edge neighboring. And for node neighboring, you can differ in every timestamp that is of an edge update that is adjacent to any one vertex. Okay, so what are some challenges in the continual release model that we do not have in the static setting? So the first thing is, in the static setting, we're only releasing one solution at a time. So there's only one release. You only care about the differential privacy of this one release. So unlike the static setting, in the continual release model, you have T releases. So if you have an edge that differs early on in the stream, then each release after that point in the stream will lose privacy, because now that edge just differs for every induced subgraph later on in the stream. Okay, so what this means is, if you want to take composition, which is a technique for DP, if you want to do just composition over potentially T releases, you could result naively in O of T over epsilon error. So this is the most naive thing you can do. We have to somehow solve this problem. So there are 3 works for graph continual release in the past. And all of these works focused on releasing numerical solutions for many graph problems. So these releases are only the sizes of the graph problems. They do not release any sort of vertex subsets, anything of that kind. So only the values of the sizes. So here's a number of problems they looked at, so including minimum spanning tree size, minimum cut size, etc. So I'll go over very, very quickly the approach that these works took previously to solve these problems. I'll use some differential privacy terms. If you don't know them, I'll redefine some of them later on in the presentation. So what they did is they have this function which takes a graph, so it could be a prefix of the stream. So a graph induced on the prefix of the stream, takes a graph and computes the exact value of the count as a solution. So again, this function f takes a graph and computes a value. Then they compute the difference sequence on adjacent prefixes, and then they add Laplace noise with sensitivity of the difference sequence. So this is a Laplace mechanism with sensitivity of the distance sequence. And then the prefix sum of the distance sequence is then the approximate solution at each time step. Okay, so they were able to also reduce the error using something called the binary tree mechanism and the sparse vector technique. So I'll define the sparse vector technique a bit later on. And they can do this on no neighboring streams using this very common technique of projecting to bounded degree graphs. Okay, so specifically, they require bounded degree graphs in order to return polylog and additive error. Yes. Yes.
Every time step, I need to be within like that additive error.
Yes, that's right. Every time step is all of that additive error with high probability. Yes. Right. So approximation is for every time step. Okay. So all these two works require bounded degree graphs. This work was able to expand the definition to nearly bounded degree graphs. So nearly bounded degree graphs is defined in terms of the number of nodes with unbounded degree is at most polylog n. So nearly up to polylog n nodes, nearly bounded degree. Okay, so there are some caveats with these approaches. The first caveat is these functions require exact values. So because they require exact values, it requires storing all of the edges. So these are not sublinear space differentially private streaming algorithms. They require storing theta of m edges. Okay, so you cannot achieve sublinear space guarantees in the number of edges, as in non-private online streaming algorithms. The second caveat is you can only return the values of solutions instead of vertex subsets. So there are some problems where you might want vertex subsets as part of your return solutions instead of the sizes. And finally, they can only return non-trivial node privacy guarantees for nearly bounded degree streams. So for our contributions, we are looking at sublinear space continual release graph algorithms. So all of our algorithms will take space that is sublinear in the number of total edges in the stream. The second thing is for some of our problems, we're going to return vertex subset solutions in addition to the values. And then finally, we'll also turn some of these node private algorithms and then have the guarantees for bounded arboricity graphs instead of nearly bounded degree graphs. So bounded arboricity is a strictly larger class of graphs than bounded degree graphs. And then we also give the first continual release algorithms for this problem called K-core decomposition. So let me just go over our contributions very quickly, and I'll describe in detail two of these results. So the first problem we look at is this densest subgraph algorithm, which is defined as this problem where you want to find an induced subgraph S that is within your input graph G with maximum induced density. So induced density is defined to be the number of edges in your induced subgraph over the number of vertices. So in this example, you have a densest subgraph with density 3/2. So we give edge DP results. So DP results in edge neighboring streams that returns a vertex subset. So it matches what's known in the static setting, static DP setting, with sublinear space, so O tilde of n over epsilon space, sublinear number of total edge updates in the entire stream, with a 1 plus eta multiplicative approximation. So the additive approximation is some polylogs over epsilon. So it matches the best known continual release algorithm up to some polylog factors in the additive approximation. And it also matches the non-private algorithm, streaming algorithm, up to some polylog additive error. Okay. So our second result is K-core decomposition result. So K-core decomposition is defined very informally as a decomposition of all the nodes in the graph into what are called cores. So each K-core is a maximal induced subgraph with the induced degree at least K. So here's a decomposition of this example graph into cores. And the K-core number is just the number associated with the K that is assigned to. So we also give a sublinear space algorithm that gives a 2 plus eta approximation and a multiplicative approximation and log cubed n over epsilon additive error. So there doesn't exist any continual release result, and it matches the non-private result up to a 2-factor in terms of the multiplicative approximation. But we also have some static results in static DP. So it matches up to polylog and a 2 plus eta approximation in the multiplicative factor.
Question.
Yes.
What is the error here? Like, is it Or I thought like you're partitioning the graph into pieces.
Yes. So the definition for k-core, so what we're releasing here is a core number for every vertex. So the core number, the exact core number is the k associated with the core that is part of. So approximation is on the number that's released. So you're guaranteed a multiplicative approximation on each number that is released by every node. And so that's a multiplicative approximation. And then the additive error is also guaranteed with high probability on each number that's released by every node. Yes?
And the space dependence on the eta, yes.
Space also depends on eta. So yes, that's all of the eta that we assume in this paper, we assume it's some fixed constant. So we don't show the eta in the bounds, but the space does depend on eta. Okay, and then we also released the maximum matching size. So for maximum matching, you actually cannot differentially release a private set of edges. So for any differential privacy algorithm, you cannot release any private set of edges. So that it does not ensure privacy if you release edges. And for maximum matching, you want to find a matching of maximum size. For this result, we have truly sublinear space. So we actually give space that is log cubed n over epsilon. So sublinear even in the number of vertices in the stream. With this particular upper bound, so this upper bound is 1 plus eta times 2 plus alpha. So alpha is a public bound on what is called the arboricity of the stream. So the maximum arboricity of the stream. So we match the best known continual release result that takes linear space up to this 2 plus alpha factor. And the multiplicative result matches this non-private algorithm. And the space matches up to factors of epsilon and polylog factors. And for this particular result, we can also, and I'll show this later on in the presentation, we can also ensure node DP. So for node DP, we require O of n alpha space. So for bounded arboricity graphs, this gives you sublinear, and you also get this approximation factor. But the difference here is this alpha bound shows up in the additive error. Okay, and using the same technique with a public alpha bound, we can also obtain an implicit vertex cover. And an implicit vertex cover is you release some amount of public information such that every edge knows which vertex covers it. So instead of releasing the set of public vertices that is in the cover, which we don't know how to do differentially privately, you release some public information, and then every edge knows which vertex covers it in the solution. And there are no known node DP algorithm for this problem. So we solved this for the continual release problem, and our solution also works for the static setting. And you can compare our solution for vertex cover in node DP to the best known edge DP algorithm. Yes? One shot. Yes, that's a good question. So our result here is for the streaming setting where you only release one solution at the end. So it's not for every release at every timestamp. Okay. And finally, we have some improved lower bounds for edge DP. So previous lower bounds, we were only able to show a lower bound of omega of log t in the additive error. So we increased that lower bound to a t to the 1/4 factor for fully dynamic edge DP streams. So fully dynamic also includes deletions. Okay, so that's all the descriptions of the results. But as I mentioned, I'll go into detail 2 of our algorithms for 2 specific problems. So as the theme of this workshop, our main technique is graph sparsification. And because we've been talking about graph sparsification all of this week, let me just go through this in 30 seconds. So graph sparsification basically finds a small subgraph of the input graph. You determine some property of the sparsified graph and use it as an approximate answer for the original graph. The sparsification can be deterministic or randomized. The main thing that I want to emphasize that the randomized approaches that we use include various edge sampling techniques. Okay, so previous work have used sparsification in the differential privacy setting. So they've used it in the static DP setting and the sliding window DP model. But it's a lot more challenging to use graph sparsification in the continual release model because errors can compound as you go later on into the stream. So the first basically sparsification algorithm that was used for bounded degree graphs are these time-aware projections. And these time-aware projections takes an arbitrary stream and produces a stream satisfying some public degree bound. So every vertex has a degree bounded by this D. And it also satisfies this property that every part of this sparsified stream, for every prefix that is D bounded, the prefix of the sparsified stream matches every D bounded prefix of the original stream. But unfortunately, the sparsification technique can only assure good approximation factors when the stream has bounded degree. So we want to be able to do sparsification for general graphs and not just bounded degree graphs. So let me give you a simple example of how that error can occur with some simple sparsification techniques. Okay, so consider this very simple sparsification procedure. So suppose that we are just removing all the edges adjacent to nodes with degree greater than D. So D is some public bound. You just want to remove all the edges adjacent to any nodes with degree greater than D. So what this would ensure is that you get a graph with degree upper bounded by D, this public bound. So now we have an edge neighboring stream. So this edge neighboring stream differ by this AV. So what happens if we sparsify this graph? Well, we obtain graphs which differ by D edges. So we basically enlarge this edge edit distance from the original stream into a larger edge edit distance. And basically the edge edit distance goes linearly into your additive error. So if you enlarge this gap, your additive error can only increase. So in this example, previously, your graph G has degree 3. So you don't remove these edges here, but here it has degree 4, so you remove all of the edges. Okay, so what we need for sparsification in the continual release setting is we want to preserve edge edit distance, which is the number of updates that differ between two streams after you do the sparsification. Okay, so the sparsified streams should only differ by a bounded number of events. So deterministic algorithms, this definition is pretty simple. For randomized sparsification algorithms, basically you want to define it in terms of a coupling of the randomness used by the algorithm, such that the output streams, if they're neighboring, differ by a bounded number of events using this coupling. Okay, as an example of this, we're going to take a look at first the sublinear space densest subgraph algorithm. So the results that we mentioned before are as follows. We return a vertex subset with these approximation and space usage. So you want to use the uniform sampling idea. And we basically use this uniform sampling idea with quite a few changes. So let me first explain this uniform sampling idea in the non-private setting. So in the non-private setting, you basically uniformly sample edges from the stream, such that you obtain O of n log n size samples via some appropriate probability p. So the eventual number of edges in your sample is O of n log n at the end of the stream. And then you find the densest subgraph in the sample, and you return this vertex subset as the densest subgraph in your original stream. So you can scale up the value of this densest subgraph by 1 over p for the size. So there are some challenges when using this algorithm, the continual release model. First of all, the original algorithms are one-shot algorithms, so they release solutions at the end of the stream. So that means that each edge is only used once in the solution output. Whereas in our setting, we need to release answers at every step of the stream. So that means that we need to adaptively choose the sampling probability And we also need to ensure that the adaptive sampling probability that we choose is edge edit distance preserving, as we defined earlier. Okay, so one way to adaptively choose this sampling probability is pretty standard. Okay, so when your number of edges exceeds some 1 plus eta times the number of edges you've seen previously, you just rescale your sampling probability by a factor of 1 over 1 plus eta. So basically, you rescale your sampling probability to n log n over m now, where m now is your current number of edges that you've seen. So it's equal to 1 plus eta times the number of edges you previously recorded. So unfortunately, you cannot do this exactly in the continual release model, because naive scaling could result in different probabilities for different edges. So naively scaling using this procedure here could result in different probabilities for different edges, so it's not distance preserving, or it's not easy to show that it is distance preserving. And this is an example of some amount of compounding errors in continual release. Okay, so we need to somehow ensure that the probabilities of sampling are the same using some coupling for your neighboring streams. So to ensure this, we use the sparse vector technique to determine when to reduce the sampling probability. So the sparse vector technique, I've also mentioned this before, is a DP technique for determining when a query exceeds some threshold. So this threshold query is a DP algorithm that tells you when your specific query exceeds some fixed threshold. Okay. And the main part of this is that you lose privacy proportional to the number of times your threshold is exceeded. So it doesn't have to be, it actually does not have to be some fixed threshold. It could be different thresholds. But this is a property that's very nice. You do not lose privacy necessarily for every query, but you lose privacy proportional number of times the threshold is exceeded. So here, if we use the sparse vector technique to determine when to decrease your sampling probability, now we can show that there exists a coupling between your sampling probabilities for every edge. And because a coupling exists between your sampling probabilities, now your sampled edges preserve edge edit distance. Okay. So because we can show the preserved edge edit distance, we can now guarantee our DP property. Okay. So finally, I want to talk about a final additional challenge. So the additional challenge is this SVT technique introduces some noise of O of log n over epsilon. So now you need to ensure that your noise does not increase the multiplicative approximation of your algorithm. So basically what you want is you want to scale up the additive error by a 1 over p factor. Because in order to get your densest subgraph, you have to scale up your densest subgraph by this 1 over p factor. So scaling up by this 1 over p factor essentially means your additive error also becomes log n over p times epsilon. So this could actually affect your multiplicative approximation if you also scale up your additive factor by a log n over p times epsilon. So the solution is just to ensure that every single time you return a densest subgraph, the densest subgraph has large enough size such that your additive error does not affect your multiplicative approximation. Okay, so let's just put all of this together. So putting it together, you want to sample each edge update with probability p equals n log n over n prime for some appropriately large n prime. That is some prefix of your stream. And then you use the sparse vector technique to determine when the threshold of the number of edges seen exceeds 1 plus eta times n prime. So n prime is your initial setting of m. And if the SVT is satisfied, you decrease the probability by a 1 plus eta factor. So you decrease your sampling probability by a 1 plus eta factor, and then you resample existing edges with probability 1 over 1 plus eta. And then once you have your sample, you use the epsilon dp. So this is a static epsilon dp algorithm for each sample to determine a release of a solution. But you only release these solutions at appropriate timestamps. So you don't release it at every timestamp. And to determine which timestamps to release, you use SVT again to determine if the densest subgraph has increased by a factor of 1 plus eta. So this ensures a 1 plus eta approximation. And you only increase when the densest subgraph has actually increased by the 1 plus eta factor. So you can release this via any static epsilon dp algorithm. We have a bunch of static epsilon dp algorithms that give you this densest subgraph subset of vertices. And then finally, to get the value, you scale up the value of the densest subgraph by the inverse of the current sampling probability. Okay, so that is a very high-level overview of the algorithm. And finally, to deal with the additive factor, as we said, we set the first non-trivial initial release to be when the density exceeds log squared n over epsilon. So the epsilon dp guarantee comes from the dp of the sparse vector technique. We can also show the edge edit distance is preserved and also composition over a number of algorithms. But the approximation guarantee, unfortunately, requires some very intricate turn-off bound argument that accounts for the errors from the sparse vector technique and as well as the epsilon static dp algorithm that we use. But unfortunately, due to time, I don't have time to go over this argument. Okay, but the main takeaway I want people at this workshop to take away with is that adaptive uniform sampling with SVT is basically a sublinear simplification in differential privacy that is edge distance preserving. So you can potentially use this for other algorithms besides the algorithm that we use it here. And I want to conclude with this very brief description of node DP maximum matching, which uses this concept of arboricity simplification to basically broaden the set of node DP algorithms to a broader class of graphs. So arboricity sparsification is what I call a sparsification using some upper bound based on the arboricity of the graph alpha. So arboricity is defined very quickly as the minimum number of forests to decompose a graph. And it's some measure of local sparsity. So for this example, the arboricity is 2 because you can decompose the graph on the left into 2 forests. Okay, so Solomon 16 obtained a very nice O of n alpha sparsifier for maximum matching. So the sparsifier is O of n alpha size. And basically, the sparsifier marks lambda O of alpha over eta arbitrary edges adjacent to every vertex. And they keep the edges marked by both endpoints. So basically, he showed that this the matching in the sparsified graph is a 1 plus eta approximation of the maximum matching in the original graph. So how do we translate this to the streaming setting? Well, very simply, we can just mark the first alpha edges incident to every vertex in the stream, where alpha is some public bound on the max arboricity. So in the streaming setting, in DP setting, we have to have this public bound. And the public bound, very importantly, is not actually guaranteed to be the upper bound on the maximum arboricity in the stream. If you have that guarantee, it violates privacy. So we do not have this guarantee. So it could be smaller, but our approximation only holds when it is actually an upper bound. And again, as before, we use SVT to determine when to release a new matching size. Okay, so let's take a look at this example. So we have some node neighboring streams, and you're given the public bound alpha equals 2. So in this example, you can perform this sparsification to get the edge edit distance is now alpha. So basically, you sparsified for the from an unbounded degree, vertex v. So this vertex v could be unbounded in the original stream. But after you do the sparsification, now you are guaranteed that the edge edit distance is alpha. So now specifically, we use SVT with sensitivity O of alpha to determine when to release a new matching size. And basically, the sensitivity of lambda in SVT directly translates to a lambda polylog n over epsilon additive error. And we just obtain our main result, which is an O of n alpha space algorithm with this approximation guarantee with high probability. Okay, so the main takeaway for this workshop is that arbitrary sparsification for no DP also applies to vertex cover. So we use the same sparsification technique for vertex cover for no DP, and also to DP in the static setting. So we can potentially use this for other problems beyond this paper. Okay. So in conclusion, these are a set of interesting open questions you might want to consider. The first thing is we would like to see closing the gap for fully dynamic streams. So as I shown before, we have a number of, say, t to the 1/4 lower bound results for fully dynamic streams, but we have no non-trivial algorithms for any of these problems in fully dynamic streams. Basically, a lot of our techniques break down when you consider deletions. And for both insertion only and fully dynamic streams, we want to have any sort of space lower bounds in addition to error lower bounds. So for DP, most of the lower bounds show error lower bounds, but it will be very interesting to consider space lower bounds for this reason. So many of our space guarantees includes a factor of O of 1 over epsilon. So O of 1 over the privacy parameter. It's not exactly clear that this factor is necessary for DP algorithms. And of course, because there's no factor of the privacy parameter in non-private algorithms, this factor is not present in any of these non-private streaming algorithms. So it's not clear, as I said. Is this factor really necessary for our DP continual release algorithms? Okay, so that's it. Happy to take any additional questions.
Applications for adversarial robust algorithms?
Adversarial robust algorithms. Can you define adversarial? What do you mean by adversarial robust?
So when the string can adaptively change according to the released information?
Okay. Yes, that's a good question. The question is, does this have any implication for adversarial robust algorithms? So let me answer this in two parts. So first of all of our results are adaptive. So you can have adaptive streams. Look at the results from the DP results from our previous releases. So our differential privacy guarantees are okay for adaptive streams. For adversarial robustness, that's a good question. I'm not sure if our DP results are adversarial robustness, I guess, could imply that your release solutions are also adversarial. So
When they say adversarially robust stream, they usually just mean
adaptive. Okay, so our results are adaptive. Adversarial robustness, I also have this interpretation that you can mess around with your private information. So that's not clear, but for adaptive streams, yes, our algorithms are also satisfy differential privacy. Yes.
So your results don't have a dependence on T at all in there.
So okay, that's a great question. So T we assume is poly n. So we can write all of our results in terms of T also. So it holds in terms of arbitrary T, but for simplification, we assume T is poly n. Yes.
And also, so yeah, that's for pure DP. Would you get any savings if you get like approx DP? You know, like usually you can get like better composition mechanism.
Yes. Yes. That's a good question. So the question is whether we can get better results for approx DP. I would guess we can get better poly dependencies for approx DP, because one of our polylogs, we often have this gap of a log n in terms of the additive error, and that's because of composition over log n releases. So for a prox TP, I would guess that we can save in terms of the composition over log n releases. So I think we can potentially get better log dependence in the additive error. Yes.
So you mentioned SVT for both your node and edge DP settings. And that's a good way to handle the case where you're releasing like private solutions or values, real numbers. But you also talked about results where you actually release like graph.
Yes.
Can you give an overview of your techniques for Q release methods for releasing like the entire graph?
Yes. So the question is, can you give an overview of the techniques for releasing parts of the graph? So let me answer your first question really quickly. So you mentioned that we use SVT for many of our results. So to clarify, our use of SVT is only to determine when we want to release new private solutions. So as I mentioned before, if you release a new private solution for every one of your t time steps, you get a t over epsilon error because of composition. So basically, we only release a new solution when our solution value increases by a 1 plus epsilon factor. So our SVT is for determining when to release a new solution. So we only release polylog n times. So this also holds for the case when we're releasing vertex subset solutions. So the vertex subset solutions, we determine when to release a new solution. And when we release a new solution, we rerun a static algorithm or a sample to release a new solution. So the vertex subset solution just comes from running our static algorithm. And the SVT is used only for determining when we release this new solution that we get from our static algorithm.
Okay, let's thank Quanquan again.